And the three basic vector shapes that I'm looking for are point, line, and polygon. Remember, the point is 0-dimensional. I also asked you in the question to come up with an example, and everyone came up with just fine. This we'll use Melissa's test sheet as well. She's not here today. She measured a gas station can be represented with a point, and it could. If you go on Google Maps and type in gas station, you'll see points indicating that. A one-dimensional vector shape is a line. She mentioned river, that's perfect. Or a polygon is a two-dimensional vector shape. So those are the three things I was looking for: point, line, polygon. And she gave an example of a lake, which is that works perfectly. So that one, I don't anticipate many questions. That one went over really well, which is good because that's a pretty one of the basic core things that we talk about. That maybe you're already seeing this. That a lot of other things build upon these shapes, and that'll become even more evident when we start talking about analysis after spring break.
Determine how many tribes to bring out to the site.
Second question, people, I think the acronym helps. What are the 4 ways in which a map can be incorrect? And it's shape, area, distance, and direction. Right, I brought the globe in and we looked at that. So those are the 4 things we were looking for in that question. Any of those 4 things can be incorrect in a projected coordinate system. You can preserve one of them at the expense of the other 3, or you can build a projection like Robinson that is a kind of a compromise of all 4. Where none of the 4 are correct, but the total error in each are minimized. Any questions? People did really well on that. Okay, number 3, the scale question. I'll go over this because this was a challenge. And it can be tricky. That's why I put something like this on here, and I'll ask this again on the final, if I remember to. It's my current intent to put it on the final. So map scale is very important on the map. It's not uncommon at all that I'll be asked to make a map and be told what scale it should be at. So it's something that you'll have to do if you go out and become a GIS professional. It's something you'll have to consider. Or I'm asking what scale do you think is appropriate, and I have to think about that. So the question says on map A, the distance between 2 points is 5 inches. On map B, the same 2 points are 10 inches apart. So right off the bat, we can see, we know map B is zoomed in closer. So it will have a smaller number. Before you even get to trying to figure out what the number is, it will have a smaller number for the scale because you've zoomed in closer. Think of this as Buffalo, Rochester. Picture a New York State map there. Now on this map, Buffalo, Rochester are closer together, or further apart on the map. So you've zoomed in closer. So we also know the scale of this map is 1 inch equals 1,000 feet. So we know if this map, if the features are twice as far apart, the scale would be half. So 1 inch equals 500 feet. So that's probably the easiest way to get to the numbers. But that's why I usually don't, I try not to be too picky, but I was a little picky on a couple of these, I apologize. Expressed in a ratio format, if you got to the right answer, you got 7 out of 8. But the 8th point is it asks for the ratio format. And the ratio format, if you remember, we talked about is where you convert to the same units on each side. So 1 inch equals 1,000 feet. The ratio is 1 to 12,000 because there's 12 inches in a foot. So if we make both sides of this equation equivalent, we're already at inches on the left side. To get to inches on the right side, we would do times 12. Does that make sense? So now 1 inch equals 12,000 inches. And then when the units are the same, So if everyone, 1 inch equals 1,000 feet is the same as saying 1 inch equals 12,000 inches. And then with the same units on each side, it becomes just a ratio. So the original map is 1 to 12,000. That makes this map 1 to 6,000. So that's the answer that we're looking for. I think I didn't explain this. Oh, now the eraser's gone. So does everyone understand how I arrived at this number? Both in the math and kind of the general. Whenever you're doing math on a question like this, it's a good idea to do a general reality check. And in this case, the reality check would be, gosh, the map is zoomed in closer because the features are further apart, so the scale is smaller. So given that high-level kind of analysis of this situation, if you went through the map and came up with a number greater than 12,000, you would know that you did something wrong in your math. So this, I'm probably asked something like that again on the third test. And I will, should I do so, we'll talk about this and go over it again the week before the final, because I think that's a pretty important thing. Any questions? Next page. I think that people did pretty well on this. A lot of people forgot the last touch that would get you the 6 point out of 6 instead of 5 out of 6. It's a conversion from degrees, minutes, seconds to decimal degrees. So I had 30. See what I mean? I picked easy numbers for you. I had 30 degrees, 6 minutes, 0 seconds north. 76 degrees, 45 minutes. There's a minute symbol left out there. 0 degrees west. So if you remember from reviewing degrees, minutes, seconds, we know there's 360 degrees in a circle. Remember that? You remember that? There's 60 minutes in a degree and 60 seconds in a minute. Think of time or think of a clock if you have trouble remembering that, where the degree is like an hour, then you have minutes and seconds, just like you would with time. So in this case, if you think about it, and to make life easy for you, I would not worry about seconds. I made seconds 0 on both. 6 minutes would be a tenth of 60, right? So the decimal degrees version of the latitude is 30.1. So that's all set. 45 out of 60 is 3/4, if you think about that. So it's 76.45 negative. Some unfortunate people forgot that. And that's picky because I think I share this story every time, but I'll get coordinates that are positive and it ends up in Kazakhstan. Because 76 degrees west is 70 degrees west of England, or which puts us not quite the Buffalo, it's like Syracuse with that longitude, that area, I think. 76 degrees east of the equator puts you in Kazakhstan, Uzbekistan, and those type places. So it's a pretty glaring mistake if you're trying to map something. So it's important to remember, and it doesn't apply to everyone. Many of us would end up working in the Western Hemisphere, and so that's something that you would deal with all the time. You need to always make sure you have the negative. If you end up taking a job on the other side of Greenwich, you don't have to worry about that. I thought it was a typo. But not again. This is warmer today, right? But, and I'm sorry, this is probably the most picky thing I do. I'm sorry. But sometimes people got the number right and put a degrees north and degrees west, and it's not decimal degrees anymore. A key to decimal degree is that it's a pure number. Because you convert to decimal degrees because you want to do math. You want to calculate math on these, and you can't calculate math anymore if there's a degree or an n. So if you got the numbers right and put those in, my pickiness on that one, you got 5 out of 6, or you should have. Or if you forgot the negative, you got 5 out of 6. 4 out of 6 if you did the positive and then degree. So it really should be just the numbers, and she's got that right here. And that's, I should give you all a point for that. That's 75. 3/4 is 0.75. Oops. Does that make sense? So there's the conversion. I don't know if I'd ask that again or not, but that is very important. It's something that we use all the time. We'll often get spreadsheets from people that have located a feature. Here's something that did happen recently. We were looking for environmental contaminated spill sites, and someone had gotten a list of them, and wherever they had gotten them, it had a degrees, minutes, seconds on it in an Excel sheet. And we couldn't do anything with this, so we had to convert it from this to this so we could put it on a map. So this is the kind of stuff we do a lot, so that is pretty important. But the key, that last final point, remember that it's to be decimal degrees, it's a real number, no more degrees or letters. And with decimal degrees, you don't need them. You don't need the degrees anymore, and you don't need the letter. You know it's west already because it's negative. The W becomes unnecessary. It's just in the way. Any questions? Yes.
What else makes a negative west? I didn't know.
That's a good point. I think I mentioned that, but didn't review it. South.
South and west is negative.
South and west is negative. Yes. So yeah, negative. And that's actually a good point. I messed up a table because we had a project in New Zealand once, and it was completely backwards. New Zealand is east of the Greenwich Mean Line, so the longitude was actually positive, and New Zealand is south of the equator, so the latitude was negative. So I got used to doing the way things I always do and messed it up pretty badly. That's okay. So say if you end up working in China, both decimal degrees would be positive. If you're in South America, they'd both be negative because you're below the equator, but also west of the Greenwich. That's a good question. Any other questions on that? Once I think I did that one year. I felt bad. I threw people off on the south, but I decided not to do that. Where are we now? Number 5. What universal transverse mercator? This is the answer I'm looking for. I did accept people that had reasonably close interpretations of that or guesses, and that were pretty flexible. I think universal transverse mercator, but if you put universe transverse mercator, I mean that's close enough. But UTM, and of course UTM would work. So UTM, universal transverse mercator, is the projection with the central meridian and 60 zones. That's also one, I keep saying that. It's one projection we'll use a lot. Worldwide. The UTM is a worldwide projection. You're always going to be in one of the 60 zones. We're in zone, we're at the border of zone 17 and zone 18 when you're in Western New York. Questions? Number 6. We talked about what are the 4 common attribute types. We talked about numeric and non-numeric attributes maybe the second or third class. And we had 2 non-numeric. And there's all sorts of different words for this. Two different types of non-numeric attributes. The non-numeric attributes, of course, are attributes where there's no math, there's no numeric meaning to the attribute. And you had nominative, which is just any attribute about you. Your name is nominative. There's no mathematical meaning to your name. It's an attribute about you that describes you. And nominative, in that list there, county name was nominative. And zip code, that's slightly tricky. Zip code was nominative, even though it's a number. Think about it, the zip code doesn't have any numeric meaning. It's a nominative attribute it describes where that particular post office delivers mail. So there's not a numeric value to the zip code 14260. They just happen to use a number for it. In some countries, in Canada and other countries, it's not even a number. There's an alphanumeric code. There's a code. Sometimes I'll switch it up and say social security number. That's a similar thing. It's a number and it doesn't have numeric value. I'm not better than you or like have more than you because I have a higher social security number. There's no comparison or value judgment based on your social security number. It's just a random number. The other type of non-numeric attribute was ordinal. And why do I talk about this? Because it affects how we draw features. So in nominative, as I just said, there's no comparative mathematical value. It's just a name for something. So we'd often use a random color. You think about a wall map of the United States has random colors on it. Ordinal is still non-numeric, but there is a value judgment or a ranking. And ordinal was listed twice. Like letter grade is ordinal. If one of you gets an A and another person gets a B, it's not really a number, but I can say the person that got an A did better in the class than the person that got a B, even though it's not numeric. For those type of attributes, we call that ordinal, and we tend to draw those in a color ramp. I think I showed a couple examples of that. Building condition score, I use that because we've done that for real projects, where U.S. military will assign they call it red, amber, green to every building, and it represents the quality, the condition the building's in. Some buildings are black, which is worse than red. I was giving the training session, I brought up our building and it was colored black. Everyone would leave. So again, that's another thing where no one came back after break. I don't know why. It's not a number, but there is a comparative value judgment with ordinal data. A green building is in better condition than an amber building, which is in better condition than a red building. Just like a person with an A did better than a person with a B, even though it's not a number. So numeric values, we have, I'll get the easy one out of the way. Most numeric attributes are a ratio, meaning there's an absolute zero, and you can take two numbers and not only say that one has more, but compare them in a ratio. If one Bills player makes $10 million and then another Bills player makes $20 million, you can say the other player made twice as much money. You can take two numbers in a ratio attribute and compare them in a ratio. That's a fair statement. Everyone would agree with the statement about him making twice as much money. Most numeric attributes are ratio, and what we have here, average household income and temperature Kelvin, which I'll get to in a second. We had a long discussion for that day about temperature, which falls into interval. Temperature is interval, not ratio. And I mention this because if you have an interval data set, you need to be careful in your legend how you describe things. An interval number doesn't have an absolute zero, so you can't make a ratio. And the example I gave that day was if it's, I think it was 1 degree that day. If it warms up to 2 degrees, no one thinks that it got twice as hot. Because there's no absolute zero, you can't make comparisons like that with an interval number. I guess to even illustrate the point better, if it was -2 and got up to 2, how would you say, is it twice? Is it -4 times as hot even though it's warmer? That also illustrates with an interval number, you can't say twice as much, 3 times as much, and so on. The only interval listed was letter D, temperature in Fahrenheit. Celsius would have the same problem because there's not an absolute zero. And Kelvin, that we talked about, is a ratio because there is the Kelvin temperature scale has an absolute zero. It doesn't get colder than 0 in the Kelvin scale. Kelvin scales where all molecular activity stops. It's probably a bad scene. So Kelvin measures temperature in molecular activity. So if you have one temperature of 100 Kelvin and another temperature 200 Kelvin, in that case you can say that it got twice as hot. Sorry for the, well, moving away from physics class now, sorry. Any questions? Number 7 relates to number 3. This was a little easier, I think, because we weren't comparing maps. I had said, what did I say? The map scale on our map is 1 inch equals 2,000 feet. So convert that to a ratio. This is what you would have to do is remember what a ratio scale is in comparison to a unit scale. So all you would do is we have inches here. To convert to a ratio, we need to get inches on both sides of the equation, and we would do that by multiplying by 12 because there's 12 inches in a foot. So the answer is 1 to 24,000. If it's some form of this or question 3, I'm pretty sure that I'll re-ask. That's question 7. Question 8, I think I probably could have worded better. There are a lot of different answers on this. I would accept 2 different things. I think that this is one of the ones that's going to cause me to add some points back. Give an example of how you might model 2 different GIS layers in relation to each other using topology. Now I realize we talked about topology in 2 different ways. So I would accept a discussion that went either way, and I got some of both. We talked about the mechanics of topology, where you have the 2 polygons. Remember that? I think it was right at the end of the class. The 2 polygons that share a line and how that's topology. We also talked about, and we looked at rules that you can set up in ArcGIS or with some screenshots. And I talked about how a hydrant has to be connected to a water line. A county has to be located within New York State. And we remember that discussion. That's what I was aiming for more than the other way, and that's what most people did end up answering. So you could answer this by sketching this and noting how, with topology, 2 adjacent polygons share a line, or 2 adjacent lines share points. That's one way of describing topology. Or you could describe 2 real-world layers that have a specific topological relationship, like the 2 things I just mentioned. Like, for example, a town, by definition, a town is part of a county. Everyone would agree with that, right? Amherst is part of Erie County. So the topological rule would be that Amherst must fall inside Erie County. To take Amherst to put it in Korea doesn't make any sense. That would violate a topological rule. The other example that I just mentioned reuse is if you're drawing a hydrant. It has to be attached. I mean, the water's got to come to the hydrant from somewhere. So the hydrant needs to be attached to the water line. There's another example. So you have a water line layer and a hydrant layer with another topological rule. And there are a lot of good answers on this too. Or, in general, just one more. Often you might say something in a network has to be connected to other features. Like a road should be connected on either side. They don't just build a road in the middle of a field that doesn't have any other outlet. So like a 4-lane highway here that just ends at field and here. The road needs to somehow connect to the greater street network, or you would think it would. So that's another type of topology that you could mention. Does that make sense? Otherwise, never say never. They probably wouldn't do that. Now you probably tell me, oh, but it was what? The 290. Yep. Well, that's a good one. Or the bridge to nowhere in Alaska. So I was a little bit lenient with that one, and those are the two different things about topology that I had been asking for. Is there any questions on that one? Number 9, who's it really well, which is good because this is another one of those fundamental things. What is the fundamental difference between a geographic coordinate system and a projected coordinate system? the geographic coordinate system is spherical in nature. And so it's measured in latitude, longitude. So a measurement in a geographic coordinate system would be something like a latitude, longitude. It doesn't have to be a perfect, a couple people put it requires a perfect sphere, and that's not the case. I let that slide. The key point was that it's spherical. A geographic coordinate system works with the datum and ellipsoids. Actually, it doesn't have to be a perfect sphere. If you remember, and I didn't ask this question, but for the datum and ellipsoid help approximate the actual true shape of the Earth, which is not a perfect sphere. It's flattened because of the force of gravity, and of course you have mountain ranges and things on it as well. But in general, the geographic coordinate system measures coordinates on a sphere, where a projected coordinate system works with all the map projections we talked about, SADD and all that. And on a projected coordinate system, you're dealing with a flat surface with an X and a Y, measured in meters, feet, and so on. So that's the major difference between the two types of coordinate systems. It doesn't necessarily have to be. One or two people may put something like it has to be meters or it has to be feet, and it doesn't. I mean, it could be in inches or miles, and that was okay. It was close enough. But it could. The key is that it's a linear measurement. It is usually meters or usually feet. It doesn't have to be, but in most cases, those are the most convenient ways to measure. Number 10, describe the basic structure of the raster data model. This is really well on this one. Probably not a hard one. The raster data model, and some people wrote very simple answers, which I like. This is one that you can convey very simply if you want it. A raster is made up of grids. It's a grid made up of cells or pixels of equal width and height. Just what I said there is enough for the 6 points. Grid, equal size pixels. As opposed to vectors, which are geometry and have dimensions. And after tonight, we're going to talk about more things having to do with vectors. Number 11, we talked, this might have been the day before the test. Can the same feature be represented in two different cases by two different types of vector shapes? Yes. And it depends on the scale of your map. And many people remembered, I think I showed Google to present that. People must remember that because quite a few mentioned this exact example. Where on this map, we see Buffalo represented with a dot. At some point, I think I have to actually type Buffalo for it to show up. If I make this map of Buffalo, Buffalo's represented with a polygon. But if you remember, as I zoom out, at some point we hit this change in scale, and now it shows Buffalo with a point. So here, yes, the same feature can be represented with two different shape types. Not in the same layer. Google's switching to a different layer to do that. But we're representing it different ways because of a difference in map scale. Especially, say, if we zoom out to a map of all of the United States, you would never be able to see the outline of Buffalo at this scale. It would just wouldn't add any value to the map. It would and take away from the map by making it harder to read. So that's the answer I'm looking for there for number 11. Questions? Comments? The compression, I was flexible on this too. There's different formats in which people could answer. A couple people, I tried to give some credit. Some people used quad tree or a different compression method other than run length encoding, but still got it right, and I like to give some points for that. In run length encoding, if you look at that top row there, there's 4 2s in a row. So run length encoding would compress this grid by doing 2 semicolon 4. And I wasn't so interested in exact format. If you have 2-4 or 4-2, as long as you're consistent, that all works for me. And then sometimes you can't compress. There is only 1 3 that occurs. Only 1 4 that occurs. So they would do that. But then on the next line, the 6 numbers could be reduced to 2 numbers. Well, 4 numbers, really. Like that. So this is what I was looking for on run length encoding. It doesn't seem like you're saving much space, as I mentioned in class. I think of this as a grid with millions of pixels in each direction. There you can save a lot more space than you could in the example right here. List one advantage, number 13. One advantage of the vector data model and one of the raster data model. Obviously, there were a number of different advantages of each. The raster data model is simpler, one I would take. It works well for continuous data. The vector model works for discrete data, discrete shapes. I think I always use the desk as an example. The desk is a discrete shape. It has a well-defined start and stop point, where something like climate does not. Climate changes gradually. Soil type, if we're in the environmental arena, soil type changes gradually. Concentrations of pollutants may change gradually. If you have PCB contamination, in most cases it doesn't just stop like that. So it might if there's a geological barrier, but in most cases it would gradually dissipate. So raster is good for that. So there are a variety of different choices for that, and I tried to be flexible for you. Questions? Number 14. A table primary key. What is the primary key? It's one field in a table that is unique and doesn't repeat, that represents a unique occurrence of that. So if you look at number 15 below, the primary key is sample ID. The primary key also helps relate a table to another table. So I would take all those things as part of the description. So sample ID from number 15, you can see there's a primary key ID 1 through 10, each of 10 rows. For that sample ID to be a valid primary key, each of those numbers can only occur once. If there were 2 sevens, that's an invalid primary key. In fact, if you work with Microsoft Access and you set up a field as a primary key, it won't let you type in the number again. If you type 6, then try to type 6 in the next line, Microsoft Access will actually stop you from doing that. The other key point that I was looking for, and I must got the point across, which is good, is that the primary key should be something that doesn't change. I gave all those examples of trying to change different tables. The primary key should be immutable or dumb, meaning it's without meaning. Like for example, your name is not a good primary key because some of you go get married and end up with a different name. So that primary key did change, so that's a bad primary key. Also, probably everyone here has someone else in the planet. With 7 billion people on Earth, there's probably someone else with your name somewhere, or maybe a lot of other people with your name. So name is not a good primary key because it could repeat. So and this applies to United States citizens, I imagine other countries have something similar. Your Social Security number is a good primary key. When a child is born in the United States, the Social Security Administration issues a Social Security number to the child. That's a unique number that doesn't apply to any other person and never will. So that's an example of a dumb primary key. So there's no value. Your Social Security number is just a random number. Any questions on that? One more, and this is the one that usually makes my popularity drop. I would like to ask this question. You guys did pretty well on it. There's a lot of extra information put down sometimes. I was just looking for the key. I think I need to reword it to stress that I'm looking for one specific thing. I think the way I worded it led you to do more than you needed to. So I'll have to fix that for next year. Basically, all I'm looking for is to normalize chemical. For Melissa, she did the same thing. She had a lot of stuff on here, but she has the right answer right here. To normalize chemical into you create another table. This I won't ask again. I mean, I'm tempted to, but just you're done with this forever. So that's good. Unless you take a database class. So you have another table called chemical, and by normalizing it, you remove the duplication. So for example, in these pollution samples, there were, there's 3 PCB samples taken. There were 3 TCB samples taken. So that's redundant data. This goes back to, this ties into question 14 quite nicely. So if for some reason the chemical PCB was changed, it's short for something. I can't tell you what it's short for. Poly, okay. Maybe do it.
Polychlorinated biethanol. I googled it 2 seconds ago, so I figured
Okay. Polychlorinated biethanol. Is that what you said?
biethanol.
Biphenyl, there you go. I won't make that the bonus question. We'll pick something other than that. So say your boss comes to you and says, I don't want you to abbreviate PCB, I want you to spell out polychlorinated biphenyl. Then you'll wish that you did normalize your table, so you're not typing polychlorinated biphenyl in every single row. When it's normalized, we have a unique ID in the chemical table, and now all polychlorinated biphenyl samples are number 1. So this is all I'm looking for. If you continue to normalize, then you would go back to your core table and just put 1 wherever there's a PCB. So now, if that request comes into me, it's like, no problem. I'll go to the chemical table. Yes, I'm peeking. There, I just changed it once. No need to go and type that thing I'll repeat a time. So that's the point of normalization. So this is all I was looking for. So I'm going to have to reword that to make it more clear so you don't do extra work. But many people, I felt bad I had a lot of extra stuff in there, which was really cool. But then also did have the right answer here. And this is worth a full 10 points. Though I'm tempted, I don't think, like I said, I don't think I'll ask about this one again. I think you can. It's not really GIS. I mean, this is a database question more than a GIS question, but especially more and more, the two things talk to each other enough that I think it's worth covering in the course. And then finally, the bonus question, you can really tell who is here. The 100th meridian was the longitude mentioned in that current rock hit by Tragically Hip that they just released now, right? It's not classic rock. If you put that that's classic rock, you lost 10 points. No one's so bad. So if you have any questions, we'll do now. Why don't we take, it's early yet, but we'll take a quick break. Come back, we'll do the lecture, and then be done for tonight. And let me know if you have any questions.